Okay, so thanks all again. So hopefully you sent out a message to Piazza last night, I think, about midterm 2 is in a week's time. And that will cover, it will be the same format as the first midterm, except we'll give you significantly more time to make sure everyone has plenty of time to finish and then to upload it onto Gradescope. And it's going to cover everything up to Tuesday's lecture. So today's lecture onwards, you will never have an exam on. You also never have homeworks on, so to some degree you can treat it more as sort of special topics like seminar style stuff. But that doesn't mean stop coming to the lectures. There's some cool things we're still going to cover. In particular, we got 3 lectures on quantum error correction coming up, which is really as important as anything in this class. But so last lecture, we talked about entropies and how they're defined and certain properties of them, particularly strong subadditivity. Today, we're going to talk a bit about what can be thought of as the operational, sort of almost physical meaning of entropies, like what operational meaning means how they control what you're able to do with quantum states. And this is the topic of quantum Shannon theory. It's a big field, not as active as it once was, but like there's a huge number of seminal and like technical results in there. So we're just going to sort of skim the surface of it, try and give you guys some sense of how it all works. So the field of sort of Shannon theory was started, basically created pretty single-handedly by Claude Shannon, one of the great 20th century scientists, or maybe you want to call it a scientist, maybe like mathematician, information theorist, but that understates him since he created the field. Computer scientist, possibly, I don't know. And he basically single-handedly made the abstract notion, if you will, of information into a sort of concrete, well-defined thing. And the way he did so is he defined it in terms of communication between two people, right? Like yeah. To talk about like quantifying information and so on, you need to distinguish state of someone not having information and the state of them having the information. The sort of easiest, like physical, practical way to think about that. So you imagine someone sends them a message containing information, and you want to know how much information they got from that. Okay, so in particular, you can define the information content of a message as, roughly speaking, the number of bits needed to communicate it. This is slightly less precise than our definition of surprisal with probabilities last time, but we'll see how it connects to it. But this is a very practical definition. But it's important when we define this that it's sort of the minimum. Sorry, why did I have? It's the minimum number of bits, right? So in particular, if I send some long-winded message saying, hi, how are you guys doing? Hope you're well, blah, blah, blah. I could have just deleted all of that and just told you, I don't know, next midterm, next Thursday. And that would be, a lot more efficient way to communicate the same information. So the information content wasn't actually as big as it might have seemed from the long message I actually sent you guys yesterday. And even if I'd compressed it right down to sort of the most efficient English sentence to get the job done, the English language is not sort of perfectly efficient. For example, sort of E is much more common. Than Q, and so on. This means that actually still more compression is possible, even if you got the down to the sort of most efficient English language statement that will say the thing you want. Okay, so one of the most basic theorems in Shannon theory, this is just classical Shannon theory, so far no quantum mechanics showing up, is about how much compression is possible. And to answer this question is like, to make it practical, you need to make some assumptions. There's really two important assumptions you make. The first, which is really the big one, is the center of Shannon theory. This was Shannon's idea that made all these questions practical. So we're going to assume we have some message. It's built out of letters. And we'll assume that each letter in that message, so each E or Q or whatever it might be, is independently and identically distributed. Okay, this is called IID for short. In other words, have some probability P of having an E. This is the sort of same for every letter in the message, and is independent of the other letters, right? So it doesn't matter what the other letters are, the conditional probability is still the same. Okay, so this is obviously not a realistic assumption for like English sentences, right? Like there's correlations between which letters naturally pair up together and so on. If there's a Q, that makes it much more likely that the next letter will be a U and so on. But it's a simplifying assumption that makes the problem tractable, and sometimes you just need to do that. The second assumption we're going to use, which isn't going to seem very important first, but in sort of general Shannon theory is pretty important, is that everyone, the person sending the message, the receiver, all have infinite computational power. Okay, so that means if we're sort of compressing a message or something like that, we don't have to worry about how difficult the computation is to decode the message or to encode the message. We just assume everyone can do that. You know, if there's some map that does it, then they can do that instantly with no cost. Okay. Okay. So this, if we make these assumptions, then we can show this very famous theorem called the source coding theorem. So let's say we have a message containing little n letters. Then I'm not going to be precise about my statements here. You can be a bit more fancy, but roughly speaking, if we define the minimum compressed length of this message to be n bits, then the limit as n goes to infinity of the length of the compressed message divided by the length of the uncompressed message is equal to just the entropy of each letter. Okay. And what I mean by the minimum compressed length is that we need to be able to recover the original message with high probability, with probability that tends to 1 as the number of letters little n tends to infinity. Okay. Any questions on the sort of statement of that theorem? I haven't tried to formalize it as a mathematically precise thing, but yeah, any questions? Okay. So let's sort of call this a proof. It's not going to be a formal proof, but it's going to be very much a sketch of the proof of how this works. And the way it works is basically that it uses the law of large numbers. That's really all of Shannon theory, or traditional Shannon theory at any rate. Now there's fancier stuff, but traditional sort of Shannon theory and quantum Shannon theory all just takes advantage of the law of large numbers and the fact that you have this large number of independently distributed letters. Okay. So the law of large numbers says that with high probability, which we could quantify if we wanted to, the sum over I of the log of the probability of getting the letter xi. So we have some string of letters x1, x2, ... xn. Okay, and this is randomly chosen from the IID distribution. Okay. So then the sum of with high probability, the sum over the logs of each of those probabilities of the actual letters that show up, okay, is going to be given by the number of sort of samples we have, so little n, times the expectation of log of the probability. Right, so this is just, we have a sum over a load of independently identically distributed random variables. In this case, log of p of xi is given by n times the expectation plus some order square root of n thing. Okay, this is just the variance. If I add up a load of independent things, grows as square root of n. The sum grows as n. Okay. In other words, p of x x1 ... xn equals, which is equal to the product over the p's of xi, because they're all equally and independently distributed, which is equal to 2 to the minus the sum of the logs. Sorry. Get rid of that minus sign. Okay, product of log pi is product over pxi is 2 to the sum over log pxi. And this is then going to be equal to 2 n times the expectation of log p of x plus order square root n. Okay, what's the expectation of log of p of x? Well, by definition, it's just minus the entropy h of x. Okay, so with very high probability, if we randomly choose a string, randomly have look at some message, then that message will be a message that had probability 2 to the minus n times h of x plus some subleading amount. What is, okay. We're going to call any message for which this is true a typical message. Okay, what this means is that, yeah, so the statement above is now the statement that with high probability, if we have some random message we want to send, then it will be a typical message in as much as its probability with respect to the distribution that each of the letters were chosen from is like 2 to the minus n times h of x plus something subleading in n. Okay. So with high probability, the message will be typical. How many typical messages are there? Well, they all have probability 2 to the minus n h of x plus o squared n. And that means, and the total probability of getting any of them is close to 1. So that means there must just be 2 to the n times hx plus o squared n. Okay? So the total probability of a typical message okay, now we can show this claim above that the sort of minimum length of the message is little n times the entropy per letter. Okay, so we're going to first show achievability so that you show that you can send a message of that length, which compresses the thing we want. Okay, i.e. if n over n is greater than h of x, then compression is possible. Okay, so how do we show this? All you do is you choose a distinct encoded message for each typical message. Okay. This is possible because the number of typical messages, sorry, the number of allowed encoded messages is 2 to the big N. Whereas the number of typical messages is 2 to the N h of x plus something subleading. So we can assign a different encoded message to every typical message. Okay. If the message happens to be an atypical message, we just give up. We just say the compression failed, that message didn't work. But this only happens with some very small probability, right? Messages with very high probability, a random message will be typical. Okay. And then, you know, if Bob has a dictionary, relating each sort of typical message to an encoded message. You can recover the typical message and we're done, okay? So that's how we compress this message into any big N that's bigger than h of x. What about optimality of this encoding? If we want to show that if n over n is less than h of x, then it's not possible. Well, each encoded message can only represent like one message, right? So one input message. So if we only have n bits that we're sending, then we can only correctly decode 2 to the n different input messages. But with high probability, the actual message was typical. And hence the probability, it was 1 of at most 2 to the n decodable typical messages. Is 2 to the n times the probability of it being any of the individual typical messages, which is 2 to the minus nhx plus O square root n. So this is much less than 1. So the decoding will fail with high probability. Any questions about how that proof worked and like what the question was and yeah.
How could a message be atypical in the first place?
Yeah, so maybe, let's say our message is like English language message, okay? We'll ignore the fact that the ID approximation is not valid in the English language. But then your actual message for some reason that you want to send is like Quentin is a queen, Quentin is a queen, Quentin is a queen, like lots and lots and lots of times. So it just has some like huge atypical number of Qs in it, right? So that would be an atypical message because the probability of like choosing that message, if you're sampling from the distribution where I don't know what fraction of letters are Qs in the English language, some tiny fraction, right? And instead, like, I don't know, say 10% of the letters just happen to be Q. Okay, so that's a message that would be atypical, and then you wouldn't be able to decode it. You wouldn't be able, your compression wouldn't work. It wouldn't know what to do with it. But that would basically never happen. As long as you make this assumption of each letter being independent and identically distributed, and your message is long enough, then the probability of having that atypically large number of Qs and hence a really small message probability is just vanishes.
So like a typical message has to have like almost one of each letter coming out the same amount?
So it's in proportion. You have some probabilities, right? So let me just do an example down here, right? Example. Let's say your message is a series of bits, right? But each bit the probability of the bit being 0 is like 99%, right? But the probability of it being 1 is only 0.01. Okay. A typical message would be something like 0, 0, 0. Like, let's say 50 zeros, and then a 1, and then another 150 zeros, and then a 1, and then so on, right? Like roughly 1% of the message will be ones. Okay, an atypical message would be something like 1, 0, 1, 1, 1, 1, 1, 1, 0, 0, 1, 1, 0, right? Just some message that doesn't have any particularly close to 1% ones. Yeah, this is theoretically possible. Each of these messages, there's a large number of these atypical messages. Each is theoretically possible. But the total probability of having some atypical message that we want to send is very small. Did that answer your question?
Yeah, so IID doesn't mean that each letter has to have, like, say in this case 0.5, 0.5, they can have different probability.
No. IID does, yeah. So IID does not mean not each letter, there's two meanings of each letter. There's each letter in the message and yeah, so this does not mean that the distribution is sort of equiprobable. Not each letter in the alphabet is equiprobable, right? That would so we can have P of E not equal to P of Q, but what we assume is that if you have a Q, if you have your first letter is E, then the second letter is distributed, conditioned on that, is distributed about exactly the same way that it was before you looked at the first letter. So it's still like, I don't know, 20% probability of E, 15% of T, whatever the list of English letters are. That makes sense?
Yeah, okay, thank you.
Cool. Thanks for the questions, everyone. Okay. So this is really the sort of real meaning of the Shannon entropy. It's the sort of rate. Yeah, it's the compression rate per sample from the distribution. We have some probability distribution, and we're sampling from it lots of times, and we're trying to send the information about all the samples, and it's the rate at which we can compress those results. Okay. Okay, so that's just about classical stuff. This lecture is going to be about quantum Shannon theory. So let's talk about what the sort of quantum analogous thing would be. So in this case, what we want to do is we want to imagine choosing n states independently from some ensemble where we choose the state, have the state psi I with probability pi, okay? And these are going to be not necessarily orthonormal. Okay. And what we want to do is we want to compress those states into the smallest possible Hilbert space. In other words, we want to take those states, we want to send as few qubits as we can from Alice to Bob. While still having it that Bob is going to be able to recover the original state with high probability. Okay, so there's a theorem for this too. Again, we're not going to state it precisely, but basically says that the limit as n goes to infinity, sort of log d, log the dimension of the Hilbert space, or sort of the number of qubits needed for the compressed state. Divided by n is going to be equal to the von Neumann entropy of the density matrix rho. Okay, where rho is, of course, sum over I pi psi I. Okay, so let's again see a very high-level sketch of how you would go about proving this. The first step is going to be to diagonalize rho so that it's equal to write it as sum over I, so qi phi I. Okay, so these two expansions of rho as an ensemble are not going to be the same. One is like the actual ensemble that we prepared the states in, and we want to recover what our state actually sent through successfully. And this one is just the eigenvalue decomposition of rho. Okay. So the full density matrix of the n states, where we're averaging over the whole ensemble, is just rho tensor n. Okay. And this, for exactly the same reasons involving the law of large numbers, right? The eigenvalues of rho tensor n are just like eigenstates, just products of phi i's, right? On each of the n copies, different I maybe on each one. And the eigenvalues are just the products of the q's. This is just exactly the same setup with some probabilities and law of large numbers as before. So this is going to be dominated by typical eigenvalues, typical eigenstates, with sort of eigenvalue, log of the sort of full eigenvalue can maybe called Q, which is just equal to the sort of sum, well, equal to sort of log Qi1 plus log Qi2 ... Right, so this is an eigenstate, phi I1, phi I2, ... phi In. Okay, just some value, some phi I for each of the n copies. And this is going to be equal to minus n times the entropy, von Neumann entropy of rho, plus an order square root n correction. Right, this is just exactly the same story we had in the classical case, that if you randomly sample from the distribution, you look at a random eigenvalue, then its probability, its eigenvalue will be 2 to the minus n times s of rho plus some small correction. Okay, so then what we're going to do is we're going to define a projector P to just be a projector onto the typical subspace spanned by those states.
Could I ask a quick question about the decomposition we did of the density matrix?
Yep.
So we were saying in the first case, I guess the difference is that the psi i's in the first case aren't guaranteed to be orthogonal.
Yeah. So we had some actual ensemble, right, of probability pi of getting psi I, and that's what we're actually wanting to recover, right? We're wanting Bob to end up with the state psi I if the original state was psi I. Okay, but those psi i's aren't necessarily orthonormal. So there's a separate thing where we just take the density matrix, take the thing we added up, and then look at its eigenvalue decomposition. And that will be orthonormal, but that's not the actual ensemble we're interested in. Is that clear?
Yeah, thanks.
Awesome. Okay, so if we take this projector onto the typical subspace, then it's easy to see that if we take the trace of rho projected into this typical subspace, we don't actually need one each side because p squared equals p, but whatever. All right, this is going to be the sum over sort of typical, typical I1 to In of Qi1 all the way up to Qin. And because we claimed that probability is very close to 1, like with probability very close to 1, we will it's dominated by typical eigenvalues, then this is roughly equal to 1, right? It's bigger than like 1 minus epsilon. Okay. But in turn, we know that rho can be written as a sum. I should really have used different letters for these things. Let's change this I here to a J for clarity. So J labels the different states in the non-orthonormal real ensemble we care about, and I is being used for the eigenvalue ensemble. Okay, so this trace of P rho P is also equal to sum over J1 all the way up to Jn of trace of P psi J1 ... psi Jn psi J1 dot 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 psi jn. Okay, that's just linearity. Can then do this trace explicitly. It's just the sum over j1 jn of sorry, I should have had a pj1 dot 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 pjn out the front here. I dropped that accidentally. So we have a pj1. So this is the probability of that state in the ensemble showing up times the norm of the state psi j 1 dot psi jn projected into this typical subspace. Okay. Each of these terms is less than or equal to 1. So if this whole sum is less than or equal to 1, sorry, is close to 1, then it has to be the case that with high probability, a randomly chosen J1, Jn has psi J1, psi Jn, P, psi J1, psi Jn, roughly equal to 1 as well. Right? So if each of the terms, the P's add up to 1, and the inner products are all less than or equal to 1, and so the only way you can get that full sum to be greater than or equal to 1 is if you know, with most of these psi p psi's are very close to 1. Okay. Otherwise, it's just you just lose too much, and you can never get the whole sum to be close to 1. So a protocol for quantum compression is just going to be the following. If the state is in the typical subspace, well, let me write this slightly differently. We're just going to measure whether the state is in this typical subspace. If it is, we can just send it to Bob. Using n times s of rho qubits. Okay. If not, we give up. But we know from the fact that trace of rho times p is very close to 1, that this has very small probability. And we know from the fact that with high probability, this trace of psi1 to j1 to jn projected into the subspace is close to 1. The project into the subspace doesn't change that state very much. And so if we succeed, measurement doesn't change the state very much. Okay. So with high probability, the state that Bob receives is approximately the original state. Okay. Any questions on how that all worked?
What do you mean by measurement doesn't change state much?
So it just means that P psi I1 dot 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 psi IN roughly equals psi I1 psi IN. Right, so we know this must be true with high probability because we know with high probability, then this is true, right? And the projector can't increase the norm of the state. So so this state is, you can think of this as an inner product between psi j1 to n and p of psi j1 to n. And one of those is normalized, one of them is subnormalized, so that if their inner product's close to 1, they must both be basically the same state. Is that clear?
When you do the trace, shouldn't it be norm squared? How do you just get the norm?
No, so when we do the trace here, doing the trace just means you take the stuff from the beginning and move it over to the end, basically, right? So it just becomes, we just have, if it's the inner product, which is the norm squared. If you want to define the norm as the square root of the inner product.
Okay.
But it's the inner product between this normalized state and this new state, which has smaller norm, is close to 1. That means they must be basically the same state.
Yeah, all right.
Any other questions? This is quite a technical lecture today, by the way, and we're not going to follow up on it in future lectures. So if you don't understand all the details, don't worry about it. Just try to get the vague sense of the tricks involved. Okay. Guess we should go on. Okay, so the other thing I want to talk about today and try and give you some sense of how the proof works is something called, it's the quantum version of the noisy channel coding theorem. Okay, so what we want to do is we want to send some classical message. I'm going to assume it's like a perfectly compressed classical message. So we can't make any savings by, like we did before, by compressing it more. Okay, so it's like each message, equally likely we want to send any message, any string of 1s or 0s. But the only way we have to do that uses some sort of communication method that is noisy. Okay, so there's a classical version of this, which is one of Shannon's original contributions, very, very famous. We're going to think about the quantum version of this. So what's going to happen is that Alice is going to input some state into a quantum channel N, okay, which may be noisy. And then Bob's going to receive something, some noisy version of the original state, and they're going to try and use that to send a classical message. Okay, so this is going to be looking at the classical capacity of a quantum channel. There's also lots of other things you can ask about, like the quantum capacity of a quantum channel. But we're just going to focus on this one example because it illustrates a lot of the tricks involved. And yeah, it's probably one of the easiest ones to work with. Okay, so Alice has a message, which we can label little x, that we can think of as just a string of like 1s and 0s, or just some number between 0 and 2 to the n. And what's she going to do? Well, the most general thing she can do is she can just prepare some density matrix, row X, which state she prepares depends on X. She then sends it through the channel N. And finally, Bob can do a measurement. Bob needs to get some classical information out. So the most general thing you can do is do like a generalized P of EM measurement on N row X. When he does so, he's going to get an outcome, little y. And we need the sort of probability that y is equal to x be very close to 1. Okay, that's the aim of the game. They're trying to successfully send this classical message with high probability. Okay, if we assume x is randomly chosen. Okay, otherwise, if we only have to have it work for a single value of x, then we can obviously always do it with probability 1, because Bob secretly knows what x is already, because there's only one possibility for it. But x is randomly chosen across equiprobable distribution over all possible inputs. Then we're gonna need to use this quantum channel and like learn something about it. Okay. So the key trick is that we can describe this measurement process, as we saw a few lectures ago, by a quantum channel called M, where M, acting on some state sigma, is just going to be the sum over the possible measurement outcomes y of trace of sort of some a projector, or maybe more generally positive operator, pi of y times sigma times just ket y bra y, right? So this represents classical outcome, right? We're treating it as a density matrix, just because we were using density matrices already for the quantum part, but because it's just a sum over different values of y, we can just treat it as it's really just a classical thing. Okay, there's no off-diagonal terms in the matrix. Okay, and necessarily, because this is a quantum channel, it will have some Steinstring representation, where m of sigma can be written as trace over E of V sigma V dagger, where V is some isometry from B to Y tensor E. Okay. Y is just a Hilbert space built out of the possible measurement outcomes. Okay. So we can write the sort of initial classical quantum state. So this is sort of hybrid state that includes both the classical message X that we're trying to send and the state rho X that's being prepared as rho AX, sum over X, P of X, which in this case is just equiprobable over X. The state rho X that Alice prepares, right? That's system A, tensor X. Okay, so this is a state that knows that if the message you want to send is X, then Alice prepares rho of X. Okay. Can then define a state rho BX as just equal to sum over X, PX, N rho X, tensor X. Okay, so now all we've done is we've put Alice's state rho x through the quantum channel, and this is now, sorry, should be Bx. This is now a state that labels, what Bob's, the state Bob's receives is, which is n rho x, and the value of x, and it includes like the probability distribution over all of those possibilities. Okay. Can then we have this measurement channel, okay, which we break down into 2 steps. First, there was an isometry. So that gives us the state rho y ex, sum over x, p of x, v, n rho x, v dagger. It's x. And finally, do a partial trace over little big E to get just the state on y and x. And we demand, if the protocol is going to exceed, that this is roughly equal to sum over sort of x and y, p of x, just a delta xy. So we have x equal to y with high probability, system y being in state y, and the original thing x still in state x. Okay. So this is just tracking the density matrix through all the different stages. So this is sent from Alice to Bob. These two are collectively the measurement, which we represented using a Steinspring, as isometry plus a partial trace.
Sorry, where did the delta function come from?
Oh, this came from the fact that we're assuming that the protocol succeeds, and so we always have y equals x with high probability, right? Like Bob's measurement outcome, we're assuming ends up being equal to the original message that Alice wanted to set. Is that clear?
Yes, thanks.
Okay. Okay. So now we can start looking at some entropies. In particular, the mutual information between x and y, just equal to a sum over x, px. So so this is equal to s over rho x plus s of rho y minus s over rho xy. So the reduced state of y is just sum over px y, as is the reduced state of px ket y bro y, as is the reduced state of x, as basically is the reduced state on xy, just with x equal to y. Okay, so all these things are all equal. And they're just equal to sum over x, px log 1 over px, which of course is just the number of bits in the message. Okay, because we're assuming here p of x is equiprobable over all the possibilities. Okay, so this is just saying that because the measurement outcome y ends up being the same as the initial input x, then they're perfectly correlated. They have maximal mutual information between them. Okay, here is, so someone asked last time why strong subadditivity is important. Here is the time where strong subadditivity comes in this case. Basically any proof in quantum Shannon theory, like one direction, will normally involve doing something like this. What we say is now the mutual information between x and b for the state rho bx. Okay, we want to compare that to things. Okay, so going from rho bx to rho yex, that was just an isometry. And an isometry can't change entropy because it's just a unitary suppose we're like treating something as a subspace of a larger thing. So this is equal to rho YE, to the mutual information between YE, sorry, between X and YE. But then strong subadditivity means that the mutual information between X and YE is greater than or equal to the mutual information between X and Y. Okay, which is the number of bits as before. So what we've shown is that the mutual information between X and YE, X and B has to be at least as big as the number of bits in the message. What is the mutual information between X and B? Well, it's equal to the entropy of just rho on B, right? Plus the entropy of B conditioned on X, sorry, minus the entropy of B conditioned on X. That's one definition of the mutual information. This is just the entropy of N acting on sum over X, Px rho X. This thing you can check is sum over X, Px times the entropy on N of rho X. Okay, so it's the difference between the entropy of the mixture and the expectation of the entropies of the states in the mixture. This whole thing is called the Halevo information. And what we've shown is that it upper bounds the number of bits in the message. Okay, of course, what this upper bound is depends on what your rho x's are, but for any protocol, the number of bits sent is upper bounded by this quantity for whatever rho x and px and happen to be. And that means in turn that using any protocol, it's always upper bounded by the max over all possible probabilities px and states rho x of this quantity s of n rho minus, I'm using shorthand here, rho is just equal to sum over x px rho x minus the sum over x px s of n of rho x. Okay, so we've shown that we have an upper bound on the number of bits we could possibly hope to send, which is, given by this maximization. This thing has a name. It's called the Halevo information of the channel, or chi of the channel n. Okay. So we've shown an upper bound on how many bits we can send, but that's not enough. We want to know actually how many bits we can send. We want to know the full, the actual capacity. And with a single, if we're only able to use this channel one time, then we generally can't achieve this upper bound, right? So this is a useful, easy to compute quantity that can easily tell you the sort of max amount of classical information you could possibly send through the channel. But it doesn't actually tell you exactly how much you can send. However, with some large number n uses of the channel n, it is the case we can send sort of NR bits for any rate R less than chi of n. Okay, so just like with the compression, when we go to this have a large number of uses of the same thing, large number of the same state, same distributed state, large number of like uses of the same independent uses of the same channel to send stuff from Alice to Bob, then the situation gets much simpler. Okay, and I'm just going to give a very high level sketch of this. Why this is.
A quick question first.
Yep.
Previously, we were talking about the mutual information of x and y, and you said that was approximately equal to s of rho x plus s of rho y minus s of rho xy.
Yep.
Why is that approximately equal?
Sorry. Yeah. So this should be an equality.
But the idea is that the rho of y x
because exactly we only have to have like y is equal to x with very high probability, so that rho y x being that is only approximate. Cool.
I see.
Really, there's a lot of technical stuff in this lecture. I tried to like simplify it as much as possible while still meaningfully doing some quantum Shannon theory. But it's a lot of content and technical stuff. I just want to give you guys sort of a vague feel for how this all works. You shouldn't feel that you have to like understand every detail of it. I really want to emphasize that. Okay, but I do want to give you some sketch of how you can achieve this upper bound given by the maximum of this quantity. Okay. So what we're going to do is we're going to let choose some ensemble, px rho x, that achieves the maximum in the definition of chi of n, right? So we have some ensemble that has maximal mutual information between x and b. And we're going to use that ensemble to construct codes that let us send these classical messages at this maximum rate. Okay, so we're going to encode each message that we want to send as a typical string sort of x1 to xn messages we want to send, like so the state is going to be rho x1 tensor rho x2, so on up to rho xn. So each different message will be encoded as one of these states, where it's going to be a typical such state, i.e. we're going to have the sum over I of log pxi is going to be equal to n times h of x plus some order square root correction. Okay. So that's going to be our classical messages that we were going to send to Bob. So then Bob's going to receive a state after these have all been sent through their respective channels. And the state Bob receives is going to be n of rho x1 tensor n of rho x2, so on up to n rho xn. Okay, because each of these rows just independently gets sent through a copy of the channel. Now, this state is going to get dominated by the usual arguments about the law of large numbers, by eigenvalues that have the following size. Okay, where the log of the total probability of the eigenvalues, well, what's it going to be? we're going to have some contribution for sort of each value of x, each possible value of x. Okay, not necessarily the ones that appear here, but like each of, say, x could be 0 or 1 or 2 or 3, right? We look at how many row zeros we have. Okay, we have n0 row zeros. Just going to say that's going to be some fraction of the total n rows that we have here. And that sort of n0 copies of n row 0 is going to be dominated by eigenvalues that have sort of log p from the row zeros. It's going to be equal to n0 times s of n row 0 plus order of square root n corrections. Right, and similarly, we have to look at the contributions from the row 1s. That's going to give us n1 times, sorry, this shouldn't be 0, n1 times s of n of row 1, similarly for row 2, and so on, okay? Just sum up over all of them. But of course, we also know, because we chose these row x's typically, then these nx's, just the number of row x's in the state, is going to be equal to the total number of density matrices in the state times the probability of each one being x, plus again some order square root n correction. Okay, so this log p is just going to be, sorry, should be a minus sign here, minus n times sum over x px s of n acting in row x. That was one of the things that showed up in our Halevo information, so that's pretty helpful. Okay, i.e. state is sort of dominated by a subspace of eigenvalues and that subspace is going to have dimension 2 to the n times sum over x px s of n row x, which is just 2 to the n of h of b, sorry, s of b conditioned on x. Did I write h back here? Yeah, that's all good. Okay, just the conditional entropy of b conditioned on this classical label x. So now the question is, if we have a large number of different typical strings, how many can we have and still be able to distinguish all of the states n row x1 to n row xn? Okay, so we're just going to randomly choose a large number of typical strings and hope to be able to distinguish them all on once Bob receives them by doing measurements. Well, if we average over all typical strings, we'll end up with a state n row tensor n, and this is dominated, sort of has a sort of flat spectrum. Yeah, it's dominated by eigenvalues where p is 2 to the minus n sb. plus order square n, right? We no longer have the conditioning on x, i.e. it's sort of evenly spread out over a subspace of dimension 2 to the n times SB. Okay. So how many different typical strings? How many distinct states row x1, row xn can we fit in that subspace? Well, just at a very crude level, we might guess the number that we can fit is the ratio of the dimension of the whole space that everything ends up in, even if we average over all of the states, divided by the sort of dimension of the subspace that each one takes up on its own, right? And this is, of course, equal to 2 times n times the Halevo entropy plus something like subleading. Okay, and this is turns out that this is correct. As long as you just randomly choose different typical strings to define your row x1s to row xn, then you know this works, and we have the answer. So we have success. Yay. The classical capacity of a quantum channel, the sort of rate at which you can send information through a quantum channel, it's just this Halevo entropy, Halevo information, chi of n. Unfortunately, still not quite right. Because when we proved, there's a bit pulling wool over your eyes, because when I proved the upper bound of how much information you get through is just a Halevo information chi n, then we were only looking at one use of the channel, right? We weren't considering the situation where you can only use channel one time, where you can use lots of copies of the channel and you want to know the rate at which you're sending information through per copy. So really, our actual upper bound isn't chi n. It's the limit as n goes to infinity of 1 over n times chi of n copies of n, right? That's just taking our upper bound for the one use of the channel and applying it to this new situation where we have some large number of uses. This is called the regularized Halevo information. And if the channel was classical, it's been a known fact for decades that this would still just be chi of n, right? So classically, it's easy to prove. This is equal to chi of n. And for a long time, like people tried to show this was still true quantum mechanically. They couldn't do it, but they they really struggled to find any evidence that it wasn't. For a long time, people really hoped that this would actually be true classically, that it was still just equal to chi of n. But eventually, after a lot of effort, it was shown that it can be very slightly untrue in quantum mechanics. Like you can gain, like the most people have ever shown the difference is like half a qubit or something. Like it's tiny corrections, but they can be shown to exist. So yeah, actually, this is the real upper bound, is this limit n goes to infinity thing. The good news is we can also show that the regularized Slavo information is achievable, that this better upper bound can still be achieved. It's still like actually the right answer. And the way we do that is just apply all our arguments from before to chi of like n copies of n, right? We just start with something on n copies of n, and then we just go through the exact same motions. But this sort of regularized Lavo information involves like some large number n, like arbitrary many copies of the channel. You have to consider all inputs to this like arbitrary large system. It's not something that can ever be computed. Completely explicitly. You can't like, unless you have some other trick that lets you prove you found the limit, you can never know for sure that you've reached it. So this made a lot of people very sad. And there's still some hope that there's some like better thing that's like equal to this that doesn't involve taking a limit of n. But I think at this point, most people have sort of given up on that. Okay. So yeah, I'm basically going to leave it here. Just some comments. Other capacities. We just considered the sort of classical capacity of quantum channel. You can also have the quantum capacity, i.e. the number of qubits that can be sent. You can have the entanglement assisted capacities for both classical and quantum. Where you can have access to bell pairs shared between Alice and Bob. And you can use that to help. And it turns out this one actually, you don't need to do this limit over n thing. You can just work out an explicit formula. And yeah, okay, that's all I'm going to say about quantum Shannon theory. Next time, we're going to move on to completely new stuff. So if this was all a bit technical, then don't worry. Any questions, though, before we end?
I did have a question.
Yep.
At the end, when we're proving this Halevo bounder, at least giving an idea for it, you took the ratio of two things. Could you say again what the reasoning for considering this ratio?
So let me write them here. So this is the, this is the subspace, which like n copies of just n of rho, n copies of the like average input is all ends up in this subspace, right? So this is roughly speaking every state we're sending is in this subspace. And each possible state has support on this size subspace. Right. So each possible message, you imagine we have some big box. Okay, each of the points in this box represents a different dimension, right? So each distinct message we want to send in there, we're like using up some of the states in the box to like to sort of, to like our measurement outcome has to say, oh, if we measure any of the states in that box, then we conclude that the message was X, right? So we can't use them for anything else. So let's try that again. So this little box has size 2 to the n. And S, a big condition on X, and the whole big box that all of them have to fit in 2 to the n S of B. Okay, so it's just a question of how many different boxes you can fit in there without things starting to overlap and you being unable to distinguish them all. Make sense?
Yeah, I think so.
Yeah. Okay, any other questions?
I guess I did have one more hypothetical question.
Yep.
So are some of the attempts that people use to prove these like Holobo bounds in the n goes to infinity limit similar to what the tricks people use to calculate the Renyi entropies when like n goes to infinity with like replica tricks and things like this?
So the way you prove these things properly, they do often involve Renyi entropies because Renyi entropies can sometimes be simpler to put bounds on. It's a different n going to infinity. You mean like a Renyi entropy with n going to infinity? The like Renyi n going to infinity, or you mean a Renyi entropy on a large number of copies? It does involve looking at Renyi
entropy on a large number of copies.
Yeah, it's basically those sort of bounds. Yep.
Okay.
Yeah, exactly.
Nice.
Okay. Awesome. Let's leave it here.